In 2025, ESA's Gaia mission mapped 1 billion stars and found a wave, not a metaphor, an actual vertical displacement rippling across 50,000 light-years of the Milky Way's outer disk, 700 parsecs tall, displacing stars by 2,300 light-years from where they should be. Something massive hit our galaxy, and this is the scar. 3 questions emerged immediately. What could move millions of stars in perfect synchronization across half the galaxy? Young giant stars, Cepheid variables, stellar beacons we use to measure cosmic distances, all moving together, all tracing the same wave pattern. Here's what makes this discovery particularly unsettling. The wave is coherent, organized, extending from 45,000 to 50,000 light-years from the galactic center. For perspective, this is equivalent to discovering that every city on Earth is rising and falling by 10 kilometers in perfect synchronization without any of them feeling an earthquake. According to ESA's announcement in early 2025, this wave is distinct from anything we've seen before. Not local star formation, not spiral arm structure, something bigger. But the data revealed an unexpected pattern. The wave's timing doesn't match any known galactic event. Let's establish what Gaia actually measured, because the precision here is staggering. Microarc-second accuracy. That's measuring a human hair's width from 1,000 kilometers away. When astronomers analyzed the vertical positions of young stars across the outer disk, they found systematic displacement, roughly 700 parsecs, 2,300 light-years of organized motion. These aren't random wanderers, they're tracing a pattern. The Radcliffe wave, a local undulation we discovered earlier, spans 9,000 light-years. The Great Wave dwarfs it, 10 times larger, operating on scales that require a common cause, a single perturbation event capable of setting the entire outer disk oscillating. According to Live Science and Forbes reporting on ESA's findings, this isn't gradual drift. It's synchronized motion, like a stadium wave, but cosmic scale. The implications extend beyond stellar cartography. If young stars are displaced, the gas clouds from which they formed must have been displaced first. This wave isn't just moving stars, it's sculpting the raw material for future star formation across a significant fraction of our galaxy. This challenges core assumptions in galactic dynamics. We thought disks were stable. They're not. They can oscillate for hundreds of millions of years, which brings us to the critical question: what hit us? Theory 1. The Sagittarius collision. The Sagittarius dwarf spheroidal galaxy is being torn apart by the Milky Way right now. It's crossed our galactic disk at least twice in the past billion years. ESA hypothesizes one of these passages, likely 300 to 900 million years ago, delivered the gravitational slap that launched the Great Wave. The physics is well understood. When a satellite galaxy crosses a disk, it excites collective oscillation modes. Millions of stars respond together. Ripples spreading from a stone dropped in water. Sagittarius is massive enough. The timing roughly aligns, but this explanation faces a critical challenge. The wave's geometry is too clean, too coherent. Sagittarius crossed at an angle. Would that really produce a wave this organized? Theory 2. Dark matter subhalo impact. A 2024 Archive paper titled Dark Galactic Subhalos and the Gaia Snail explores another possibility. Cold dark matter theory predicts our galactic halo contains thousands of invisible clumps, subhalos, ranging from millions to billions of solar masses. No stars, no light, pure gravitational influence. What if a dark subhalo plunged through the disk more recently than Sagittarius? The vertical disturbance would appear spontaneous. No visible culprit, just the gravitational wake of something we can't see. The appeal? It explains the wave's sharpness. A compact, dense subhalo delivers a sharp impulse, more bullet than sledgehammer, exciting specific oscillation modes cleanly. However, this model struggles to account for one observation. If massive dark subhalos regularly cross the disk, we should see multiple wave patterns. Why does Gaia primarily see one dominant wave? Theory 3. It's not one event, it's all of them. One emerging hypothesis suggests the Great Wave is a superposition, multiple perturbations layering their gravitational signatures across hundreds of millions of years. Galactic disks possess natural oscillation frequencies, like a drumhead vibrating at specific tones. Sagittarius crossed, a dark subhalo passed. Tidal interactions with the Large Magellanic Cloud added perturbations. The result? A complex interference pattern, waves reinforcing and canceling depending on timing and location. The mechanism remains elusive. 3 competing hypotheses await new data from Gaia Data Release 4 in 2026. Here's where the physics gets intricate, and where the answer likely lives. Most astronomers now favor a hybrid explanation. 500 to 900 million years ago, the wave propagated first through the gaseous disk, not the stars. This is the gas-star coupling hypothesis. Molecular clouds respond faster to gravitational perturbations than stars because they're collisional. Gas particles interact through pressure, amplifying waves on shorter timescales. The young stars Gaia observes today are tracing the frozen-in pattern of their birth clouds. It's like watching footprints in snow. The snow moved first, the walker followed the path. The physics here operates at scales rarely tested. Collective gravitational modes in systems containing hundreds of billions of stars evolving over timescales longer than complex life has existed on Earth. Current radio telescopes lack the sensitivity to map vertical gas motions across the entire outer disk, but the square-kilometer array, planned for the late 2020s, will test this directly. If gas clouds at different galactic radii share the same vertical velocity pattern as young stars, it confirms gas coupling. If they don't, we're back to pure stellar dynamics, or something more exotic still. There's one final piece to this puzzle. What if the wave isn't ancient history? What if it's still propagating right now? Remember that question from the beginning, whether we're witnessing a frozen echo or an active wave. ESA's Gaia Data Release 4, launching in 2026, will answer this directly. By measuring stellar motions with triple the current precision, astronomers will detect whether the wave is propagating, damping, or being driven by ongoing perturbations. If it's still moving, we'll see phase shifts between stellar populations of different ages. If it's static, we're looking at a gravitational fossil, the snapshot of an event hundreds of millions of years old. The numbers describe a universe stranger than our models predicted. Remembers the gravitational trauma of its violent history. What seemed like cosmic stability turned out to be a slow-motion sea, with waves measured in millennia rather than seconds. ESA's Gaia Data Release 4 in 2026 will reveal whether the Great Wave is propagating, damping, or driven by something ongoing. Subscribe to track the data as it arrives and explore how astronomers will test the competing models: Sagittarius collision, dark subhalo impact, or superposed perturbations. Next video, how do you measure invisible dark matter subhalos using only starlight? We'll break down the methodology turning Gaia's maps into dark matter detectors. In Cosmos We Trust.